Hello, my name is Justin Young, and today my research partner Aidan Scudder and I are going to take you down the path of how we were able to model nonlinear partial differential equations using physics-informed neural networks. The overall goal of this video is to touch on some basic understandings of neural networks and specifically how you're able to apply that knowledge of neural networks into a physics-informed neural network. Today's agenda goes as follows. We'll start things off with some basic concepts of feed-forward neural networks. We'll discuss what a neuron is, what activation functions are, what loss functions are, and finally what backpropagation is. Then we'll switch gears into the physics-informed neural networks portion of this video, where we will discuss the overview of physics-informed neural networks and specifics about the case study of the 2D heat equation, talking about the problem definition, code implementation, results and analysis, as well as challenges that we faced. And finally, we'll leave a slide for additional learning resources for those who are interested. All right, now let's jump into some of these basic concepts. So a neural network is a type of machine learning algorithm, and it's inspired by the human brain. A neural network takes in input data in a similar way to how our senses provide information to our brains. Like our brain processes this information, a neural network does too. It has multiple layers of artificial neurons, each carrying out a mathematical operation. These layers are designed to recognize patterns within the input data. Once all this processing is done, we get an output or a prediction or a decision, much like our brains make decisions based on the information that it processes. In another similar fashion, just as we learn from experiences and improve over time, neural networks also are able to learn. They adjust their internal parameters based on the results of their decisions in hopes of improving accuracy of their future predictions. Now let's dive deeper into what a neuron is in a neural network. Well, each neuron in a neural network receives data. This could be input data in the case of the neurons in the first layer, or process data from the preceding neurons in the subsequent layers. Each neuron carries out a mathematical operation on the received data. It multiplies the data with its weights, adds them up, and passes this sum through an activation function. The result of this processing is then transmitted to neurons in the next layer. In essence, a neuron in a neural network is a tiny data processor performing calculations and passing on the results. However, collectively, they form a powerful system of learning and making complex decisions. Now, let's talk about activation functions. The purpose of an activation function is to introduce nonlinearity into the output of a neuron. This nonlinearity allows neural networks to model complex patterns that linear functions cannot. Activation functions determine how much signal a neuron should also pass on to the next layers. Essentially, an activation function takes the weighted sum of the inputs, applies a specific mathematical function to it, and then this transformed output is then passed to the next layers of the network. So the next topic of neural networks I'd like to touch on is the role of the loss function. Well, essentially, once the model makes a prediction using the input data in its current set of weights and biases, we need to be able to evaluate how accurate this prediction really is. And to do so, we have a loss function. During the optimization of the loss function, the derivative of the loss function with respect to the model's parameters, or the weights and the biases, is calculated. These derivatives can then indicate to us how much a small change in each of these parameters would affect that loss. In the image above, you can see how the tweaking of the parameters allow for the balls to essentially find lower minimums given different parameter. All right, now let's discuss the role of backpropagation. Backpropagation is an algorithm used to minimize the error that was identified by the loss function. The role of backpropagation is able to do so by adjusting the weights and biases of the entire network. Backpropagation calculates the gradient, or the derivative, of the loss function with respect to each weight and bias in the entire network, essentially determining how much each weight and bias contributes to the overall error. Before we switch gears into the physics-informed neural networks portion of this video, I'd like to wrap up the basic concepts with this cooking analogy. This analogy will help us learn the key discrepancies between a traditional neural network and a physics-informed neural network. I'd like you to imagine that you're a chef trying to create a new dish. You've got a recipe that tells you what ingredients to use and in what proportions to use them. This recipe is analogous to the weights and the biases in a neural network that determine how the input data is processed. As you are cooking, you might taste test the dish to decide to adjust the ingredients. These adjustments are analogous to how a neural network uses backpropagation and the loss function to fine-tune the weights and biases based on the difference between the network's predictions and the actual data. So now I'd like you to imagine our traditional neural network as the talented chef preparing a dinner. And a physics-informed neural network is that same chef preparing that same dinner under specific dietary restrictions. Both the chef and the physics-informed neural network start with the same knowledge of basic operations, but the physics-informed neural network now has additional guidelines to follow. In the case of the chef, you must consider the dietary restrictions now. He substitutes and adjusts ingredients to maintain the integrity of the flavor while adhering to those dietary restrictions. The physics-informed neural network uses a modified loss function. It still wants to make the most delicious meal possible, but it also has to satisfy now the dietary restrictions or the physical loss. If the network does stray too far from these restrictions, it's able to learn and adjust itself. Now let's dive deeper into physics-informed neural networks. Physics-informed neural networks are advanced neural networks that incorporate physical principles into their frameworks. They use a modified loss function that ensures their predictions represent these physical laws. Some key distinguishing features are that PINNs still retain the same pattern recognition capabilities of traditional neural networks, but they also inject real-world context into their predictions, resulting in more robust and reliable outputs. Now let's explore how PINNs impact the world of physics through their enhanced loss function. The enhanced loss function of the PINN framework integrates the additional term derived from the physical laws of the loss function. This enhances the model's accuracy by providing a more refined data representation that respects the governing laws of physics. There's also a composite loss. This is the key ingredient of the physics-informed neural network that balances the two main discrepancies of errors arising from the differential equation computations, as well as the deviations in the neural network's outputs. In balancing these discrepancies, a physics-informed neural network improves their prediction accuracy while also ensuring that these predictions align with the fundamental laws of physics, offering, once again, a more robust and reliable model.
Hi everyone, my name is Aiden. Now that Justin's introduced neural networks and PINNs, we'll now focus on a specific application, the 2D heat equation with hard boundary and initial conditions. This case study provides insight into how PINNs can be used to model complex systems commonly encountered in engineering and scientific disciplines. Let's move forward to explore the details of this problem and the approach we took to address it. In this part of our study, we aim to engineer a PINN to forecast the time-dependent 2D heat distribution. Our primary goal is to create a model that can predict how heat distributes over time in a 2D space. The inputs we're working with are the spatial coordinates x and y and time, t. The expected output from the network is an accurate prediction of the temperature distribution, denoted by capital T. The constraints our network must align to are the 2D heat equation PDE and the initial and boundary conditions that we lay out. The loss function we're utilizing for this problem is a composite loss function, which means that it includes the PDE residual and the residuals from the boundary and initial conditions. The end goal of this problem is to minimize the total loss of the network, resulting in precise and physics-consistent predictions of temperature. With a clear understanding of our problem definition, we can now turn our attention to the implementation of the PINN to address our specific case study. This implementation brings together the elements we've discussed, from spatial coordinates and the time inputs to the intricate loss function that aims to minimize the total error. For those interested in exploring the full code and delving into technical details, you'll find the link in the description. This will provide you with an opportunity to examine our approach more closely and even try it out for yourselves. As we delve into the code implementation, it's essential to outline the tools and libraries we utilize to bring our physics-informed neural network to life. Here's a snapshot of our deep learning stack. First, we chose Python as our programming language for its versatility, especially in scientific and numerical computing. We also used DeepXDE, which is a Python framework that was instrumental in solving our differential equations using PINNs, It handled the setup of the problem and the training of the neural network model. We also used TensorFlow, which is an open source deep learning framework. TensorFlow provided the backbone for DeepXDE's underlying computations in defining and training our model. We also used NumPy for numerical operations and particularly for the matrix computations in our problem setup. Last but not least, we used matplotlib to help visualize our results, and we used it to plot the static solutions to our partial differential equation and to generate animated visualizations of the solution evolving over time. Together, these components formed an integrated, coherent stack that allowed us to translate our problem definition into a fully functional model capable of precise and physics-consistent predictions. The choice of these specific tools illustrates how existing libraries can be combined innovatively to solve complex scientific problems. Now I'll go over the Bora instructions specifically for Boise State students. First, you'll need to connect to the Bronco Protect VPN. Then, using the command I've listed below, you can SSH into the Bora supercluster using your BSU credentials. Once you're in the Bora supercluster, you'll want to move to a GPU node via the command GPU session. Note that a GPU may or may not be available, so you can use another command that the computing department will give you to check what nodes are available and the state they're in. Next, you'll run your program via a script, and you can see the content of the script on the right. This is so you can run your programs on Bora in a controlled manner, since it's a shared resource. Now we can go into the code implementation. First, we'll import our necessary libraries. The next thing we'll do is we'll define the 2D heat equation PDE so that DeepXDE knows what the network should be working towards as the correct solution. You can see that the inputs to this function are x and t. X is an input vector with the spatiotemporal variables x, y, and time, and the output scalar is t. This function returns what the correct solution of the PDE is, and that's how the network can compute what the PDE residual is. Next, we'll define the spatiotemporal domain. This requires defining the space domain of our problem and the time domain of our problem. Using the geometry.geometryXtime function of DeepXDE, we can combine those two into a variable called geoTime. This represents our time-dependent 2D problem. The next thing we'll do is define our domain boundaries, and this is essentially telling DeepXDE what does it mean to be on the boundary. So it will check every point, and if using these functions, it can determine whether a point is on the boundary of the domain, and that's how it will help to enforce our boundary conditions. We can do something similar for the initial boundary by defining it as any point that is close to 0. The next thing we'll do is define our temperature field and boundary constraints. Since we've just defined what a boundary is, now we can define what the constraint on that boundary is. We can do this by initializing a function for the temperature field, and knowing that it's 0 everywhere for our problem, we can just return an NP array of 0. Now, for the boundary constraints, we know that on the right edge, we have a constant 100 Kelvin, but we want to normalize that. And so to do that, we'll just set it to 1. For the rest of the edges, we'll just return 0. Now that we've defined what a boundary condition is and what an initial condition is, and what the constraints on those things are, we can use DeepXDE's provided classes for Newman and Dirichlet boundary conditions to package that all together and make the conditions for our problem. Using those, we can define the training data that will be used to train the network. You can see that our spatiotemporal domain is passed, our PDE is passed, all of our boundary and initial constraints are passed in one array, and then the last 3 variables are the number of sample points from that geotime domain to take for each, the domain, the boundary, and initial. And you can vary the amount of, or the ratios between these values to give an inherent bias to the network to focus on learning. For example, if you gave 10,000 points to the boundary and 2,000 points to the domain, it would learn the boundary condition a lot better than the PDE. Now that we've defined the spatiotemporal domain, the PDE, and the constraints on that domain, we can initialize and train the model. We'll help the model learn by applying an output transform that gives an absolute value of all the predictions. This will ensure that only positive heat values are predicted. Next, we'll compile and train with both the Atom optimizer and the LBFGS optimizer. Combining these two ensures that we get the lowest loss possible. We used mini batching to help our model converge faster and reduce GPU memory usage. Looking at our network's prediction, we can see that our results are very close to the exact solution solved by the FEM. We can see that although we have a visually accurate prediction, we still have loss from the exact solution. On the right-hand side, we can see that the combination of both of our optimizers helps the model converge to a lower loss than just using one. Around step 10,000, the Atom optimizer stops learning, and that's when the LBFGS can pick up where it left off. Before we could obtain an accurate prediction in our journey towards modeling the 2D heat equation, we faced a few intriguing challenges that required creative solutions. Let me elaborate on two of those primary hurdles. One of them was learning the boundary condition. The right edge boundary condition of 100 was challenging for our model to learn, especially with an initial condition of 0 everywhere. Our solution was to normalize the boundary condition to 1 and scale the output by 100, which had a profound impact. Secondly, we faced a challenge implementing residual minimization biases. We found that the model sometimes converged on a local minimum that wasn't desirable. We had to experiment with adding bias to certain residuals to steer it in the right direction. The animations you see below are examples of what the network was predicting before both of these changes. As we can see from the results, these changes were key in getting the model to learn our problem. As I wrap up this presentation, I want to leave you with some valuable resources for those who might be interested in diving deeper into the subject of PINNs. These materials have guided us in our work, and they may provide insight for your own explorations. We hope that our exploration of PINNs has provided you with valuable insights and sparked your interest in the field. Our LinkedIn profiles are on the screen, so feel free to reach out if you'd like to continue the conversation. Once again, thanks for your attention and engagement, and have a great day.